I was talking to an old school astronomer the other night, one of those guys who spends his life chasing, pristine dark skies out in the middle of the Chilean desert. And he was pointing up at a string of moving lights, the Starlink train, with this look of just, well, pure, unadulterated exhaustion. To him, those thousands of blinking dots were just orbital litter, a bureaucratic nuisance ruining his view of the deep past. He just kept complaining that we're losing the stars, that the night sky is being turned into a commercial billboard for some billionaire's vanity project. But as I watched him fume, I realized he was focusing on the symptom, not the structural cause. He saw light pollution. I saw the first firing neurons of a planetary nervous system. He saw a nuisance for his telescope. I saw a fiscal guillotine descending on the financial independence of every terrestrial government on Earth. What's so fascinating is how we've all been conditioned to see this whole thing as this benevolent mission to bring Wi-Fi to rural farmers. We talk about it in these soft humanitarian terms, like it's just a faster version of the cable company. But then you look at the raw physics, the sheer mass being moved into orbit, the vertical integration, the financial strategy, and the whole connectivity narrative starts to feel like a sentimental distraction. The reality is so much more radical, and to the legacy establishment, it's far more terrifying. While the world is arguing about the night sky or space debris, a fundamental shift in the power structure of our species is happening right over our heads. Starlink isn't fundamentally a telecom company. It is, based on all the metrics we've analyzed, the first true Kardashev Type II civilization infrastructure prototype. It's this massive decentralized system that's designed to bypass the friction of national borders, to collapse the geographic monopoly of terrestrial fiber, and ultimately to fund a permanent exit from the gravity well itself. That astronomer was worried about his view. He should have been worried about the fact that the sky is no longer just a sky. It's becoming a sovereign computational shield, an uncensorable vacuum for data that is effectively immune to any law written on the ground. The planned 2026 IPO isn't just a financial milestone. It's the moment the umbilical cord to the legacy world is finally cut.
That's a perfect way to frame it. You've captured the core of this radical paradigm shift perfectly. When we move beyond the headlines and really look at the financial projections, the engineering metrics, and the legal analyses, the material, we see exactly what you just described, a structural decoupling. This network isn't just a communication medium, it's civilizational infrastructure that is actively reshaping global sovereignty and financial power structures in real time.
Okay, so our deep dive today is really focused on examining the metrics, the economic, the legal, the cosmic metrics that actually back up that bold claim, the claim that this satellite network is a genuine infrastructure prototype for a Type II civilization.
Exactly. We have to move entirely beyond the consumer service narrative and just analyze the pure physics and finance of planetary escape velocity. We're looking at the mechanism by which humanity is trying to, fund its way off planet and secure its future against all these terrestrial risks.
Okay, let's unpack this financial decoupling first. That feels like the true foundational block here. The core strategy seems to be making space expansion so profitable, so self-sufficient, that the operators can just ignore government funding altogether. We have the story of Elias, which I think really personalizes the frustration of the old world and the promise of this new orbital economy.
Elias's story is a perfect illustration. It shows how deeply the gravity well operates, not just through physics, but through institutional and financial friction. He was a veteran software architect, spent 20 years dealing with government-funded aerospace contracts. Brilliant guy, but his work was just perpetually stalled.
Stalled how? What was the actual friction point?
Well, he tells us one story about a specific 3-month period he spent trying to integrate one single line of custom code. A piece of telemetry sequencing. That one line required 3 months of security audits, regulatory reviews, congressional committee briefings, bureaucratic approvals, you name it.
3 months for one line of code.
3 months. Every single step had to pass through a dozen committees that were neither technically proficient nor commercially motivated. Innovation was just permanently deferred until after the next congressional budget hearing. That financial and bureaucratic tether is, it's a massive tax on technological progress. It defines the gravity well in a way that's far more insidious than just simple Newtonian physics.
And that institutional friction is precisely what the new private model aims to bypass. So Elias eventually moved to a private orbital venture, right? Now funded entirely by the liquidity of this autonomous orbital economy.
Exactly. He's not dealing with government contracts anymore. He's building the first autonomous refueling depot in low Earth orbit funded by private capital and the aggressive dividends of a space-based IPO.
It's the feeling he describes, the weightless freedom, when that financial tether to the ground just snaps.
That's it. His budget is no longer subject to a national flag, a political term limit, or the whims of a temporary administration. This marks the transition from government-backed aerospace, which is fundamentally slow, risk-averse, subject to political budget cycles, to a self-sustaining private industrial regime where speed, scale, and profitability are the only real constraints. This is the practical birth of the interplanetary economy.
And that desire for speed and scale brings us right to the core financial mechanism that the sources identify as financial accelerationism, or FinAc. We're talking about the anticipated Starlink IPO, but the source frames this as something much, much bigger than just a traditional corporate exit.
Oh, it is absolutely not a traditional exit. It's a strategic mechanism. It's an act of financial accelerationism. The goal of the IPO and the accompanying target of a $1 trillion plus valuation is really twofold. First, immediate resource capture from global capital markets, and second, channeling that capital into immediate self-sustaining expansion.
So if they hit that $1 trillion valuation, what does that actually do?
It allows them to systematically starve the terrestrial government bureaucracy of its relevance. It removes the need for reliance on legacy systems like NASA or the Department of Defense for foundational deep space financing. It's a mechanism designed to systematically strip the ground-based establishment of its financial influence over space infrastructure.
And that huge capital injection, the $1 trillion goal, that's directly linked to hard infrastructure, right? It's not just a number on a balance sheet.
No, it's intended to fund the deployment of the next 100,000 satellites. That scale is the physical mechanism that guarantees the sustained detachment of space expansion from terrestrial government financial systems. It's the creation of an entirely separate, self-capitalizing infrastructure loop.
And the numbers we have already, even before the IPO, they seem to validate this explosive trajectory.
They absolutely do. By June 2025, the company's valuation had already hit $400 billion. That's a growth rate of over 200 times in the last decade alone, and it's driven by real-world services. They're projecting $15.5 billion in revenue for 2025.
And the customer base is growing just as fast.
Yes, the utility's there. They reached 6 million global subscribers as of June 2025, which is a huge leap from 2.6 million just a year before that. That kind of rapid, self-funded scaling fundamentally alters the power dynamic when you're dealing with nation states.
Right, and the models project that growth to continue dramatically. We're moving from dominance to omnipresence. They anticipate hitting 23 million subscribers globally by 2035, supported by a constellation plan to grow to about 46,000 operational satellites in orbit. This isn't just a business model, it's the economics of spatial dominance.
And that dominance is achieved through a structural advantage we can call the twin engines of growth. The launch segment, the rockets, and the reusability tech directly enables the Starlink satellite business. Because they're vertically integrated, the cost structure is it's radically different from any competitor.
They're their own biggest customer.
Precisely. By the end of 2024, the launch segment is projected to account for about 60% of all functioning satellites in orbit globally. So they're both the customer and the provider. They're mass-producing their own delivery system to deliver their own product, and it continually drives down both fixed and marginal costs in a way that traditional aerospace or telecom companies, they just can't match.
This kind of economic independence, though, it inevitably creates friction with terrestrial powers. They're used to controlling vital infrastructure. We see this tension so clearly in the controversy around the FCC's rejection of that. What was it? The Rural Digital Opportunity Fund subsidy?
The RDOF application.
Yeah.
Yes, that rejection is a critical data point. It shows the resistance of the legacy establishment trying to hold on to control. Starlink applied for $885.5 million, which was meant to serve 643,000 rural homes and businesses that currently lack adequate broadband. The FCC rejected it. They cited doubts that Starlink could deliver the required speeds, 100 megabits per second download, and 20 up across the scope and size of the promised coverage area.
But that technical justification seems shaky at best, given the company's real-world performance. Critics at the time pointed out the staggering irony. When they were rejected in June 2022, Starlink already had nearly 500,000 active subscribers and was showing it could scale rapidly.
The rejection reeked of political bias. It led to widespread accusations that the government was picking winners and losers in broadband deployment, often favoring legacy terrestrial fiber networks even when LEO service was demonstrably cheaper and faster to deploy.
I remember Commissioner Carr's dissent on that.
Yes, he highlighted that the FCC applied an entirely new standard of review, specifically to Starlink, demanding immediate, verifiable delivery capabilities that just weren't applied to other RDOF recipients, some of whom, he noted, had deployed virtually no service at all.
So the core policy problem wasn't a technical failure on Starlink's part. It was bureaucratic resistance to a disruptive, non-territorial technology that would undermine the established fiber lobby.
Precisely. The argument was that the government bureaucracy was prioritizing control and the established ecosystem over efficiency and taxpayer value. I mean, consider the taxpayer cost. Those RDOF locations could have been connected using Starlink for about $11,134 per location over 10 years. Compare that to the hundreds of millions sometimes awarded to fiber deployments that can cost well over $100,000 per home to lay cable through difficult terrain. The decoupling is happening through private finance, but the governments on the ground are actively trying to use regulation to resist losing their control over foundational infrastructure.
So the financial engine, the FinAc, is designed to achieve financial autonomy.
Yeah.
But breaking the financial gravity well requires breaking the physical one. What does that industrial scale actually look like on the ground right now in terms of hard assets and logistics?
This is where we have to shift our perspective entirely, from telecommunications to heavy industrial expansion. I was reading the account of Matteo, an orbital technician working at a launch facility. He described watching massive server racks, the actual components of orbital data centers, being loaded into the payload fairing of a launch vehicle.
Okay.
And he noted they were no longer treated as irreplaceable, fragile scientific cargo that needed white glove handling. They were being treated like mundane freight, like shipping containers being loaded onto a cargo ship. That shift from science project to standard industrial commodity signals the true industrialization of the heavens that you mentioned.
That mundane nature, that's the key psychological and logistical transition, isn't it? It signals that mass to orbit, or MTO throughput, is changing from this extraordinary expense to a simple, repeatable logistical metric. And that MTO throughput is the true physical metric of civilizational expansion. This is where it gets really interesting with Wright's law.
Wright's law is the economic engine driving this physical cost collapse, and it's different from the more famous Moore's law. Moore's law is time-based processing power doubles every 2 years or so. Wright's law, on the other hand, says that the cost per unit decreases by a consistent percentage, often 20 to 30%, with every doubling of cumulative production output.
It's about experience, not just time.
It's a learning curve. By treating satellites, launch vehicles, and now orbital infrastructure components as mass-produced, reusable, and vertically integrated commodities, Starlink is capturing that learning curve dictated by Wright's law. Every time they launch a batch of satellites, they learn how to produce the next batch cheaper, faster, and more reliably.
How does that specific learning rate translate? I mean, is 20–30% aggressive for something as complex as reusable rockets?
For traditional aerospace, that rate would be wildly aggressive. But for a vertically integrated system that treats rockets almost like a software development process, iterating rapidly on hardware, the data suggests it's achievable, especially since the company is heavily subsidizing its own launch costs.
And the data on the cost collapse itself is pretty staggering.
It is. Since 2004, the cost of satellite bandwidth has dropped 7,500-fold, from $300 million per gigabit per second down to just $40,000 per Gbps.
And Starship, the fully reusable mega rocket, is supposed to accelerate that decline even further.
Absolutely. The acceleration is only increasing. Projections indicate that the launch cost could fall another 40-fold, bringing the cost down to around $1,000 per Gbps by 2028. This rapid cost collapse is the hard physical evidence that the energetic shackles of the gravity well are truly being dissolved. The long-term economic calculation for building Type II infrastructure, like Dyson swarms, becomes plausible only when MTO throughput is measured in metric tons of routine freight, not millions of dollars per kilogram.
And that enormous MTO capacity is paired with these incredible technological leaps in the orbital infrastructure itself. These aren't just slightly faster versions of old satellites.
Not at all. They're entirely new platforms. The Starlink V3 satellites, for instance, offer 1 terabit per second of downlink speed.
Which is 10 times the capacity of the earlier V2 minis.
10 times. And this is achieved through advanced intersatellite laser links and highly efficient phased array antennas. Furthermore, once the fully operational Starship V3 vehicle is deployed, a single launch is projected to add 60 TBPs of network capacity.
60 terabits in one launch.
In one go. To put that in perspective, that single launch adds over 20 times the capacity of a V2 mini launch. It can support the simultaneous streaming needs of millions of users. This relentless exponential scaling fundamentally changes the calculus of what is possible in orbit.
Okay, so this scaling leads directly to exploring orbital data centers and this concept of vacuum compute. We already have enormous data centers on Earth. Why go through the risk and expense of moving critical AI infrastructure into space?
Because terrestrial constraints are quickly becoming overwhelming, particularly for high-intensity computing like large language model training and inference. Orbital data centers address three major terrestrial bottlenecks. First, power.
Right, uninterrupted sunlight.
Continuous high-intensity sunlight. It offers reliable, massive power generation that's far easier to collect than terrestrial solar farms that have to deal with night cycles and weather. Second, cooling. The vacuum of space is a giant passive heat sink, making cooling much more efficient. And third, land use and regulation. Moving data centers off-planet avoids the complex terrestrial land use restrictions and often requires fewer national licensing agreements. It's a fast track for deployment.
So this orbital infrastructure enables advanced edge computing by on-satellite LLM inference clusters. What's the real consequence of this physical move for sovereignty and censorship?
It creates planetary-scale computational sovereignty. The physical consequence of locating compute in this vacuum compute environment is profound. Data processing becomes immune to terrestrial censorship or national licensing requirements.
So when the processing layer, where the complex decisions and model training happens, is moved into orbit,
the concept of code as speech gains a new physical defense layer. These operations are structurally immune to national AI safety reviews, data localization efforts, or state-mandated information control. It's an anti-regulatory breakthrough for thought and information processing itself, achieved by physically exiting terrestrial jurisdiction.
this independent computational framework naturally generates friction. We see the counterarguments all the time. The protests from astronomers about light pollution, the moral panic over space debris. The sources refer to these counterarguments as the voice of the deceleracionists.
Right. The expansionist view frames these concerns, the protests, the focus on debris, not as malicious necessarily, but as reactionary anti-evolutionary murmurs. The decelerationist or decel faction is accused of trying to impose artificial scarcity and stasis, prioritizing a pristine view of the night sky or near-term environmental concerns over the existential imperative of multiplanetary redundancy.
But the debris concern is backed by real physics, isn't it? I mean, there's the risk of a Kessler syndrome event where orbital debris multiplies exponentially. How does the expansionist perspective address that near-term catastrophic physical risk, rather than just the far future existential risk of the Great Filter?
They argue the solution isn't to stop expanding, but to accelerate the technology needed for remediation and active debris removal. Crucially, they argue that bureaucratic delays, like those imposed by the ITU or environmental bodies trying to limit launch frequency, are the greater planetary scale threat.
Because it leaves us vulnerable for longer.
Exactly. The core belief is that the most significant risk facing humanity is the Great Filter, some inevitable challenge, biological, nuclear, astronomical, whatever, that prevents a single planet species from reaching Type status and achieving redundancy. Every delayed launch, every satellite held back by red tape, increases humanity's exposure to that existential risk. So accelerating expansion becomes a pragmatic act of cosmic survival.
The technological and financial momentum is clearly pushing beyond national boundaries, but the legal framework is just. It's struggling to keep pace, creating this massive vacuum. This shift introduces these profound questions about territorial law and censorship. The anecdotal evidence for planetary sovereignty versus censorship is pretty compelling.
Oh, it is. Consider the story of Sarah, a student living in a repressive regime. The government, after some civil unrest, implemented a national kill switch, effectively turning off all terrestrial internet and cell service to suppress communication. She's in a remote location, holding a standard smartphone that should be completely useless.
But it isn't.
But it isn't, because the Starlink system has rolled out direct-to-cell, or DTC, technology using its V2.0 plus satellites. Her screen flickers to life. The satellite bypasses every single state firewall, every national border, and every control ground router, allowing her to send a simple, unmonitored message to the outside world. We are still here.
That one simple act of communication, it makes the technological implication crystal clear. DTC technology isn't just an upgrade. It's a physical, anti-regulatory breakthrough that overrides national borders and terrestrial internet censorship. It dissolves national sovereignty at the computational level.
It creates a severe legal landscape breakdown. The traditional legal system is entirely predicated on territorial jurisdiction, the idea that a law applies within a defined geographic border. That framework is just not equipped to handle non-territorial data processing.
Okay, let's drill down on the licensing ambiguity. Traditional commercial contracts use these vague, comprehensive terms like worldwide or global. What happens when compute moves off-planet?
Well, the traditional legal understanding is that worldwide means the terrestrial surface, the recognized nation-states and their territories. But when a company processes or stores data on satellites, courts are forced into this complicated interpretive exercise. Does worldwide include off-planet or extraterrestrial use?
So a licensor could argue that moving data to orbit is a breach of contract because it wasn't an intended use case.
They could, and they would have a legitimate argument that it exceeds the granted scope. It's an unintended use case not factored into the original licensing fee. This ambiguity is prompting a massive wave of urgent contract revisions. It's similar to the legal chaos the entertainment industry faced 30 years ago when satellite TV required redefining broadcast rights. Companies now have to use explicit language covering orbital, off-planet, or extraterrestrial uses to avoid litigation.
And the jurisdiction crisis, especially for intellectual property, seems even more complex since IP law relies so heavily on geographic location to determine where an infringement occurred.
This is the core structural weakness of terrestrial law. If AI training or large-scale data inferences are drawn from output generated on a satellite, where does the infringement actually happen? Is it the country where the satellite was launched, the country where it's registered, the country operating the ground station that uploads the data, or is it outer space itself, which is explicitly outside any national sovereignty, according to the 1967 Outer Space Treaty?
It's a legal nightmare. You could file a suit in 3 different countries, and the defendant could challenge the jurisdiction of all of them.
Exactly. Arguing that national statutes do not reach off-planet copying. It creates profound uncertainty and litigation delays. This is why you're seeing a predicted surge in the use of international commercial arbitration. It's a creature of private contract, so it offers a path to dispute resolution that can bypass the broken, slow, non-territorial court systems.
And beyond just filing a suit, there's the massive practical problem of evidence and enforcement, the discovery gap. On Earth, we rely on courts ordering seizures of hard drives, inspection of server logs. That's functionally impossible in orbit.
You cannot execute a terrestrial search warrant on a moving object 500 kilometers above the surface. A court can't easily order the seizure of a satellite. This creates a massive litigation discovery gap. Critical evidence, LLM training data, specific model checkpoints, processing logs might exist only on orbital hardware, effectively floating out of reach of terrestrial courts.
So if evidence is literally unreachable, how do companies protect themselves when using this infrastructure? What's the necessary legal prep?
They have to mandate contractual rights to all processing logs and intermediate data. Crucially, audit rights, including virtual or remote cryptographically verified audits, must extend explicitly to off-planet infrastructure. Legal teams are being told to draft contracts that assume a state of non-cooperation from the platform owner unless specific auditing is stipulated. It's the only way to prevent vital evidence from becoming unreachable.
And finally, the question of data privacy and geopolitical risk, which affects every corporation operating globally. Regulations like GDPR in the EU or PIPL in China that mandate data stay within national borders.
This is the non-territorial data transfer problem. Since a satellite isn't geographically located in any national territory, processing regulated personal data in orbit could immediately violate national cross-border transfer restrictions, even if the data originates and returns to the same continent. If a provider fails to disclose that some operations occur off-planet, their customer may be held liable for privacy violations because they failed to meet those territorial data sovereignty requirements.
Which means corporate due diligence now has to include the question, does any processing occur on orbiting or extraterrestrial infrastructure?
Absolutely. And then there's the U.S. export control factor, which is highly complex. Regulations like ITAR and EAR govern the transfer of sensitive tech and data. Transmission of certain controlled data to a foreign national can constitute a regulated export. Processing off-planet complicates this significantly. And finally, current cloud contracts and cyber insurance policies are utterly deficient. They assume all processing happens on Earth and fail to account for space-specific risks, radiation damage, solar storms, orbital debris. The contractual gaps are enormous.
Okay. We've covered the finance that funds the exit, the physics that enables the infrastructure, and the legal crisis that accelerates the decoupling. Now we have to step back and place this project within the largest possible frame, the cosmic picture. You frame Starlink as the infrastructure prototype for a Kardashev Type II civilization. Let's start in the foundational definition of that scale.
The Kardashev scale, which was introduced by Nikolai Kardashev in the 60s, categorizes civilizations based on their energy consumption. A Type I civilization harnesses the total available energy of its home planet. That's about 10 to the 16th to 10 to the 17th watts. A Type II civilization utilizes the full energy output of its star, which is roughly 10 to the 26th watts. For context, humanity currently sits at about Type 0.72. We're close to Type I, but we are nowhere near Type II.
And our source material refines this framework beyond just raw energy. It introduces the Civilization Development Index, or CDI. This index is a critical tool because it integrates 4 fundamental dimensions of growth.
Yes. The CDI is a unified framework designed to give a more holistic, multifaceted assessment of civilizational progression. It incorporates energy scale, which is weighted at alpha equals 0.35. Information scale, weighted at beta, equals 0.25, construction mass, gamma, equals 0.25, and population growth, which is delta, equals 0.15.
So energy and information are the primary levers.
Right. They drive the potential for expansion and complexity, while construction mass provides the physical capability, and population growth acts as a necessary catalyst. By construction, CDI of about 1.0 is Type I, and a CDI of about 2.0 is Type II.
Okay, let's start with the largest component, energy scale. What does the data tell us about our current energy trajectory, and how quickly are we approaching that Type I threshold?
The energy transition is accelerating. Projections from global energy agencies show a significant sustained shift from fossil fuels toward renewables. In fact, renewable energy has recently surpassed nuclear power as the leading clean energy source globally. It's showing rapid and consistent exponential growth.
And how does that exponential growth translate into a timeline for Type I status?
Well, we synthesize the projected renewable energy growth rates and assume a consistent nuclear growth rate of about 1.57%. By applying this to the refined Type I threshold for planets orbiting G-type stars like ours, which is calculated to be around 2.03 times 10 to the 17th watts, we project humanity could achieve Type I civilization status, a CDI of roughly 1.0, around the year 2271 CE.
2271, that's surprisingly soon. It's a precise date based on current exponential models. It really shows the transition is on the clock. Now for the information scale. Carl Sagan recognized that pure energy use isn't enough. True advancement requires computational mastery. This section deals with immense scales, including theoretical constructs like the Matryoshka brain.
The Matryoshka brain is a theoretical megascale computational construct. It's essentially a series of nested Dyson spheres or swarms designed to harness the entire stellar energy output 10 to the 26 watts and dedicated entirely to computation. To build something like that, material science becomes paramount. Viable components would have to include diamond, aluminum oxide, and titanium carbide just for the resilience and thermal properties.
That sounds like pure sci-fi, but we use it to calculate the necessary Type II computational threshold, which is massive.
It is truly staggering. The Type II information scale threshold is calculated to be approximately 10 to the 54th bits processed annually. This is the theoretical limit of information mastery using a single star's energy. And linear regression analysis, applied to the historical exponential growth of human data volume, shows that humanity is projected to cross this theoretical Type II information threshold by approximately the year 2274 CE.
Wow. So computationally, we're accelerating extremely fast toward that boundary, almost aligning with the energy timeline. We also have to address the qualitative element of that information mastery, the sentience quotient, which tries to measure the cosmic level of consciousness and complexity.
The sentience quotient, or skew, quantifies the bitrate processed per unit time relative to the mass energy required for that processing. It gives us a qualitative benchmark. The human brain, based on estimated processing rates, has an SQ of about 10 bits per second per kilogram. Type I civilization is qualitatively indicated by communality, which corresponds to an SQ of 20. This suggests a level of interconnected, high-bandwidth processing across the planetary population. The calculated upper bound for Matryoshka brains normalizes to an SQ of about 25 bits per second kilogram.
So the jump to Type II requires not just scaling computing power, but achieving a whole new level of integrated complexity.
Exactly. It means Type II requires achieving a level of complexity somewhere between communality, Type I, and what's termed hypersociality, which implies a collective, highly integrated computational and conscious architecture operating across stellar distances. Starlink, in this context, is the first attempt at creating the foundational hardware for that integrated planetary consciousness, the planetary nervous system we talked about earlier.
Moving now to the physical manifestation of that energy and information, large-scale construction mass. This is what the Starlink deployment is actually demonstrating right now, on a minuscule but foundational scale, the ability to industrialize mass in orbit.
Construction mass scale quantifies a civilization's ability to build the monumental infrastructure needed for stellar energy harnessing. Type II fundamentally requires infrastructure like a Dyson sphere, or the far more feasible Dyson swarm, a huge number of independent orbiting satellites capturing stellar energy.
Which requires moving beyond planetary resources entirely. We can't build a Type II structure from Earth's surface.
Absolutely not. Building a Dyson-like structure demands sourcing vast quantities of materials from asteroids, moons, maybe other planets. This relies entirely on autonomous construction, advanced robotics, and converting raw space materials into finished products in situ. The index we use, the construction mass index, or C sub m, is a logarithmic scale normalized to Earth's current construction mass, which is about 1 × 10⁻¹5 kilograms, the mass of all our buildings, roads, and infrastructure.
So what's our current projection for construction capacity, and what's the Type II requirement?
Projections show the construction mass index will reach 2 by 2100, which incorporates megacities, vast renewable infrastructure, and early space industry deployment. However, achieving stellar-scale megastructures like Dyson swarms would require a C sub m of greater than or equal to 5. Starlink's relentless scaling and cost collapse, driven by Wright's law, is the absolute precursor. It proves the initial capability to industrialize mass in orbit. It's the physical Dyson swarm precursor that validates the MTO economics required for stellar-scale building.
Finally, let's look at population growth, a key driver that is both a catalyst for innovation and a stressor requiring advanced management.
Population dynamics drive energy, information, and resource demands. Type I status requires sustainable global population management on Earth. Type II civilization status, however, demands stable, multi-interplanetary population distribution. It necessitates the colonization of extraterrestrial environments to expand the species' carrying capacity and achieve functional redundancy.
Okay, so when we put all 4 components together, energy, information, construction mass, and population, what is the final projected timeline for achieving Type II status?
Using the integrated CDI model, we project Type I status a CDI of about 1.0 around 2271 CE, driven largely by energy and information scaling. Achieving Type II status CDI of about 2.0 requires the full deployment of stellar-scale infrastructures and stable, distributed interplanetary population centers. Under optimistic scenarios, assuming no immediate Great Filter event, this milestone is projected to occur between the years 3200 and 3500 CE. The scale of ambition spans over millennium, but the seeds are being planted today.
The scale of that ambition, seeing our actions today linked to a timeline stretching over 1,000 years, it's immense. This deep dive really reinforces that initial radical premise. Starlink is not merely a communication company providing faster Wi-Fi. The convergence of exponential scaling in physics, radical self-funding in finance, and the inevitable legal decoupling reveals it to be the physical bootloader for a Type I civilization. It's unifying information and material flow on a global scale, establishing that planetary nervous system we discussed. The financial autonomy, the hard physical reality of mass-to-orbit cost collapse, thanks to Wright's law, and the legal vacuum that facilitates this uncensorable vacuum compute. All of this momentum is rapidly pushing humanity toward a post-regulatory world governed from orbit, designed to prioritize expansion above all terrestrial concerns.
And if we contextualize that current trajectory within the Civilization Development Index model, we see a clear, measurable pathway. Type I status is projected by 2271 CE, and Type II status is plausible by the 33rd century. What's fascinating, and what the long-term projections make abundantly clear, is that the entire framework, this millennia-long progression towards stellar mastery, ultimately hinges not just on breakthroughs in material science or orbital robotics. The physical capability is almost within grasp, but the long-term viability of achieving Type II rests entirely on a profound and sustained evolution in human consciousness, governance, and collective maturity to manage resource scarcity and avoid great filters. Those are conditions that, historically speaking, humanity's only demonstrated the ability to meet inconsistently. The ultimate constraint on the Type II project is not physics. It is humanity's ability to achieve profound and sustained collective maturity.